The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome to our June webinar. It is a part 2 of our Extensional Viscosity with EV Rock. This month, we're going to be investigating data analysis and interpretation. Today's webinar will be hosted by our in-house rheology experts, Dr. Stacy Elliott, as well as Dr. Zachary Imam. Dr. Elliott obtained her extensive experience in rheological knowledge through her education at Carnegie Mellon University and Princeton, as well as her experience at both Alcon and DuPont. Dr. Imam obtained his PhD in biomedical engineering from the University of Texas at Austin and spent a year postdoctoral continuing development on a bioscience project funded by the Department of Energy's Basic Energy Science program, studying the biophysical properties and functions of microtubules. And now it is my pleasure to turn it over to Dr. Elliott.
Thank you, Eden. Welcome in, everybody. Thanks for joining us again. Hopefully you were able to attend May's webinar, where we sort of introduced the idea of our EV Rock, which is our flow channel that is intended to measure extensional viscosity. So today what we're going to do, as Eden said, is follow up and give a little more details on how to analyze the data, and then also some tips and informative dimensionless groups that we can use to help interpret the data. So just a quick overview of what we're going to cover today. I am going to review a couple points that were brought up in May's webinar, just to provide some context and emphasize some points. So one of these things will be reminding everyone that our flow channel for the extensional, for the EV Rock, is it's not producing a pure extension. It is a mixed flow environment. So I'll remind you about that and why that is and why that's important. And then also talk a little bit more about some impact of this hyperbolic contraction expansion region that's placed in the center of the flow channel, and discuss that in a little more detail, and talk about what theoretically should be happening versus what is truly happening in real life. Also, as I just mentioned, it is a mixed flow environment, so this is kind of a blessing and a curse at the same time. And one of the analysis options that I'm going to discuss is how we can use the extensional flow channel to also get steady shear viscosity values from the pressure drop across the channel. And this is, beneficial in a couple of ways. One is it's really how you want to confirm performance of the flow channel using NIST traceable Newtonian standards. And then also, if you don't have the ability to do other types of steady shear measurements, you can use this to actually get useful data. And one use of this data would be if you are able to correct for this steady shear contribution and subtract it off from the pressure drop across the contraction expansion region. So checking performance, this can help you with that. And then also if you are able to correct for a Newtonian or power law fluid. And so we'll talk about this in detail. And then the final section will be discussing a variety of dimensionless groups that can be used to better understand what's happening in the flow channel and how to look at your data. So what these will include would be what we refer to as the pressure coefficient, the Reynolds number, which is probably the most well-known to people, and then also the Deborah number. Okay, so just a quick reminder then, as I mentioned, our extensional flow channel, which I have an image of here on the slide, similar in form in general to our uniform channel, but in the very center of the channel, we've introduced this hyperbolic contraction expansion. And this hyperbolic contraction expansion, as we'll discuss in a little more detail, does introduce an extensional component to the deformation. But because we still have the physical confines of the channel, this is not a pure extension. It's going to be a mixed flow because we still have at the boundaries no slip boundary conditions. To date, we haven't been able to, coat the channel so that we have perfect slip at the wall so that we can have some pure extension. So in the meantime, we have to accept that we do have this no slip boundary condition, which introduces a shear component to the deformation as well. So if you remember, the shear component comes from having this velocity gradient perpendicular to the flow direction. So that is still there. And so there is this contribution even to the pressure gradient in the extensionally dominated region in the center of the channel. Well, step back here for a second. So as I mentioned, this, we want to be aware of this, but we can kind of use this to our advantage in some instances, and there are cases where we can correct for that, which we'll talk about today. So also, let's look at the hyperbolic contraction expansion again and what it does, because what I want to talk about is what we kind of theoretically expect to happen, and then show you what reality looks like and why that is important. So the idea is we introduce this change in geometry as we move along the x direction in the flow channel. And what happens is the reason why this introduces an extension to the deformation is that volumetric flow rate Q is going to be constant across the flow path. And as we move along the flow path, as our cross-sectional area decreases, that means our linear velocity in that compression or contraction region has to increase. So the linear velocity increases as we move into this region here. And we've also plotted out theoretically what that should look like on the graph down below. So this is velocity in the x direction and then moving along the x direction along the flow channel. So theoretically, what should happen is velocity as we move along should be constant until we enter the contraction, and then it will rise in a linear fashion. And then as we move from the center point and then exit the expansion region, velocity should decline and then ultimately go back to a constant value. So theoretically, this is what we would expect from this specific hyperbolic geometry. And so this now introduces a gradient in the direction of flow, which is what is defined as an extensional type deformation. So this is acting to stretch or elongate the fluid element. So this graph below is ideally what we would expect to see. And let's then look at what really is happening there. And I'll point out that, and we've talked about this in some of our fundamentals webinars, but, when it comes to designing rheometers and viscometers, the goal is always to have a very as simple as possible as a flow field and as well controlled and defined as possible, because the rheological properties are all calculated and you want to facilitate that calculation. One of the challenges, though, with the extensional work is that that's a little tricky. And although we can introduce that extensional component, what I'm going to talk about now is that the simplicity of the flow field and the control is, not as ideal as we would like. So let's look at what the true velocity profile is. And I've pulled this from the reference that's listed below on the bottom of the slide. I would recommend this reference. It's pretty high level in terms of a lot of equations and math and derivation and theory, but it really, if you can get past that, it did a very nice job of analyzing our EV-ROC system in that regard. So I did borrow this image from them because they did some particle velocimetry to elaborate and let us know what this true velocity profile does look like in the flow channel. Okay, so as I mentioned, theoretically, we should have this velocity gradient in the direction of flow. It should be limited to the contraction expansion region. And so I've on our plot here, this top plot, this is basically the real plot of what we just looked at, what I had shown in the ideal sense, and that's the velocity as we move along the channel, and then x is the position along the channel. And these solid blue lines here represent entry into the contraction and then exiting from the expansion. So theoretically, we should have all of the gradients limited to this region. However, from the particle velocimetry, it's pretty clear, I think, and the data is the blue data points here. There's quite a few of them, so it looks almost continuous. This is the actual velocity as we move towards the channel and then into, or towards the contraction and then in and out of the contraction. And so what we can see is two things. One is that the gradient in the velocity in the direction of flow becomes non-zero quite a distance before we actually enter the channel. So that means that the fluid is experiencing an extensional component to the deformation in the uniform portion of the channel prior to actually entering the hyperbolic contraction. And also the other thing, and this is, kind of a consequence of, what I just mentioned and the sort of extension of the velocity gradient. Another thing is that the true extensional rate tends to be larger than what is actually predicted. And so we can see an example of, a real life relationship between the true extensional rate. So now I'm on the second plot, plot B. So true extensional rate on the y-axis, and then the apparent extensional rate or predicted rate on the x-axis. And so if they were equal, the data points would land on this solid line here. But what we're seeing is the true extensional rate is actually 1.66 times for this particular experiment higher than what we're predicting. So it turns out that our goal was to develop this simple flow channel, and in the general sense, it is simple, but we're not getting quite what we had hoped. So that's fine. It's just important to know that this is occurring and what it means to certain experiments that you want to do. And so one of the experiments where this is relevant is when you need to confirm the performance of your flow channel. So it's pretty straightforward when you're doing just steady shear to confirm the performance of everything, because the certificate of analysis on the NIST traceable Newtonian standards always give the steady shear viscosity. However, in this case, we don't have any certificate of analysis giving us an extensional viscosity. And also, even if we did, we know that we have some of these challenges in terms of the flow field and the true extensional rate. So we can't do what would be sort of the intuitive or maybe obvious path here. And so that would be, okay, we know that the Troughton ratio, which is defined as the extensional viscosity to the steady shear viscosity, has a fixed value for Newtonian fluids. And that for this type of extension is around 4. Because we know we have these challenges with the flow field and uncertainty in the true extensional rate, we're not going to be able to take the shear viscosity value and multiply it by a factor and then use the extensional output from the software to confirm our performance of the chip. So what we will do then is we can, however, calculate steady shear viscosity values from our pressure profiles. And this is, as we mentioned in the intro, it's going to benefit us in terms of confirming performance of the chip. But then also you can use this to get additional data for some of the analysis, and we'll talk about that in a moment. But just to show you how it is possible to also get steady shear viscosity from the data of the extensional chip, we're going to cover that in this slide. So this is just a reminder, this schematic on the top here, of where the pressure sensors are positioned relative to this hyperbolic contraction zone. And also a reminder of what the pressure profile looks as we're moving through the flow channel. So we see this, unlike the uniform channel where we would have a linear relationship with a single slope, we see this shift in slope as we move into the constriction zone and then another shift as we move out. So in terms of analyzing for the steady shear viscosity, we're just going to look at the two different uniform regions of the flow channel. So we're going to look at pressure drop prior to the constriction and pressure drop after the constriction. And even though we do know that our extensional component does extend before the entry and exit points of this center zone, the pressure sensors P2 and P3 are separated far enough away from that we can still get good readings there that they're not perturbed by that extensional piece. So we can still get quality steady shear viscosity just by looking at this uniform region before and after. Okay, so don't worry too much about the equations. I just wanted to make it clear how straightforward it is to go in and analyze the data yourself. Unfortunately, at the moment, the software doesn't do this for you because it wasn't really the main purpose of the flow channel, but it's quite easy to implement on your data when you export it into Excel. So we can just determine what is the shear rate in this uniform region just from knowing the volumetric flow rate Q and then the dimensions of the channel. So the width of the channel in this uniform zone, and then the height of the channel in this zone as well. And so that gives us what the shear rate is in before and after. And then the shear stress just comes from, as I said, looking at the slope of the line between P1 and P2, and then also the slope between P3 and P4. And then again, this other factor here is just bringing in the geometry of the flow channel, which is going to be well known. So once this is done, then you calculate steady shear viscosity as you always do, which is the proportionality between the shear stress and the shear rate. And so, as I said, this is how you would confirm chip performance using NIST traceable Newtonian standards. Also, if you're not doing steady shear measurements in another way using another instrument or one of our uniform channels, then you could use this as a way of getting some extra data from the extensional measurement. Also, if you start seeing large discrepancies between the viscosity that you're measuring from the sort of entry, before the entry or after the exit, then this could be an indicator of secondary flows or turbulence. And we'll talk more about some other indicators of secondary flows or turbulence, or when you should really be on the lookout for those. And then also, if you are able to extract this data and you find that you have a Newtonian or power law fluid, then you can actually use this information to subtract off the steady shear component of the pressure drop in the center zone, and then that gives you more of a true extensional viscosity, not a mixed parameter. Okay, so with that in mind, I wanted to move into the actual correction, an example of the correction which we had just mentioned. So to do that, I'm going to quickly just review a couple things that we talked about last month in May's webinar. So if you remember, what we do when we are doing the calculation for the extensional viscosity is we need to get this pressure drop that's really the pressure drop from the entry point to the exit point. So we have to look at a extrapolated piece of this pressure profile, this delta P sub C. And that's really all that is entry point to exit point. And because, as we've really emphasized here, this is a mixed flow situation, so it has an extensional contribution to that, but then it also has this delta P CV, which is the shear contribution. So ideally, we only want the extensional contribution to calculate our first normal stress difference. And so, just to sort of reemphasize some things that we talked about last month, in the case of, applying an extensional deformation, what we're doing is generating a normal stress. So it's the analogy to the shear deformation generating a shear stress. So it's slightly different in the extensional case. Now, unfortunately, there are only analytical expressions available at this time for this shear contribution to the pressure drop for Newtonian and power law fluids. But, that's power law fluids still, represent a fairly reasonable portion of fluids that are out there, and certainly they obey that over a particular range. However, if you have something more complicated and it doesn't classify as Newtonian or power law, then unfortunately we're just going to have to use this delta P sub C uncorrected and realize that we have kind of a mixed parameter here. But still, it's something that you can gauge in real life your samples. And then just again to review, the extensional viscosity defined as this first normal stress difference divided by the apparent extensional rate. So what we're going to do, just show a quick example of how things can change when we are able to subtract off this steady shear contribution to the pressure drop and then correct the normal stress difference. Okay, so this is an example of the correction for a basically a Newtonian fluid. And what we have here is a high concentration bovine gamma globulin solution in a particular buffer. So this is a model protein we work with quite regularly. And what we can see here on the plot, so we have the different viscosities as a function of either extensional or shear rate. And so this data down here, the circles are the steady shear data, so the steady shear viscosity versus shear rate. And then the filled triangles up here, this is the extensional viscosity as a function of the extensional rate. And this is the uncorrected data. So this particular protein solution is Newtonian over the range of shear rates that's relevant to the experiment here. As we get further out here, there is some shear thinning, but if we looked at the actual shear rates that are occurring in the extensional flow channel, it is Newtonian in that case. So this is an example of where there is a simple, relatively simple expression for this pressure drop, the steady shear contributions to the pressure drop across the constriction. And that's given, I don't want to overemphasize equations, but just to show you how it is pretty straightforward. And again, this is something that you could easily implement in Excel because, you know, as we mentioned in the seminar last month, our software doesn't know ahead of time what your sample behavior is. And so it's unable to apply these corrections. So these have to be done after the fact with the additional knowledge that you would have on the steady shear properties. So don't worry too much about the equation. I just wanted to point out that it's just basically related to the geometry parameters. So the length of the contraction, channel depth, and the channel width, both in the uniform region of the channel and then in the narrowest portion. This Newtonian viscosity of the fluid and then the extensional rate. So this is something that's very easy to implement in something like Excel or another spreadsheet type program. And we can see the relative magnitude of shift that you might expect when you actually do correct for the steady shear contribution. So we do see the corrected data drop a bit. And I didn't want to, the same process can be done for the power law fluid. It's just the expression is a little more complicated, but it still has all the components. It's basically the geometry, but then also power law index and prefactor that you get from fitting the data there. Okay, so now moving on to some of the parameters that you might want to look at to sort of guide you in how to interpret, what could be happening in your flow channel and what this might mean for the data. So dimensionless groups are quite common. They're quite valuable in rheology and I would say fluid mechanics in general, because what they are is basically looking at the relative magnitude of two contributions that can be occurring at the same time. And the different numbers are defined by the contributions that you're looking at, the relative contributions that you're trying to gauge. So this Reynolds number, this dimensionless group, this basically emerges from when you're doing the scaling analysis of the conservation of momentum equation. So conservation of momentum, these are the equations that govern fluid mechanics. So if you've ever taken fluid mechanics or momentum transport, this is where you would have seen these. So the most common one that people are familiar with is Navier-Stokes equations for Newtonian fluids. But the Reynolds number just basically naturally emerges when you non-dimensionalize these equations or scale them. And generally the biggest value that comes from the Reynolds number in the practical sense is that it can indicate when you might expect to see a transition from laminar to turbulent flow. So laminar flow being the flow where all of your streamlines are parallel, unidirectional flow, and then turbulent flow or the situation where you have secondary flows, this is where you see the transition to, the eddy currents or the vortices. So streamlines now cross. So this is the main practical benefit of the Reynolds number. And the Reynolds number is looking at the ratio of the inertial forces versus the viscous forces. So inertial forces are basically, momentum of the fluid. Viscous forces being related to the fact that you have this internal friction. And in the conservation of momentum equation, these are balancing in the relationship. And so don't worry too much about where so basically to get the relative magnitude of these inertial forces, or essentially momentum of the fluid motion, I took the terms from the Navier-Stokes equations that would represent this. And we just translate this into the characteristic scales relevant to our particular flow configuration and fluid that we're dealing with. So that's the whole idea of if you're not familiar with the non-dimensionalizing or scaling, you basically identify what are characteristic values for the different properties for your system, and then you use that to calculate the non-dimensional or dimensionless groups. So what's relevant here? So this is the inertial term in the conservation of momentum, and then this is the viscous term in the conservation of momentum equation. And so what we want to do is identify what is the magnitude of this in terms of our characteristic scales. So this is rho here is just density, and then we're going to have to identify a characteristic velocity scale and then a characteristic length scale within our flow channel. And likewise down here, it's still, needing this characteristic velocity scale, length scale, and then also the viscosity of the fluid that we're looking at. And so that gets us the Reynolds number in terms of things that we can, pull from our particular system and then calculate this. So it's just density, characteristic velocity, characteristic length scale divided by the viscosity of the fluid. So what does that look like for our extensional flow channel where we have this hyperbolic contraction and expansion? So I've rewritten it slightly here. So density is obvious, viscosity, steady shear viscosity is obvious. Our characteristic velocity scale is represented down here. And that can just be, expressed in terms of our volumetric flow rate and then the channel dimensions, which are all defined in our schematic here. And then I've replaced characteristic length scale by hydraulic diameter. So this is the way you would generally take a rectangular cross section, a flow channel with a rectangular cross section, and narrow that down to a single length scale. And the hydraulic diameter is given down here. It's just 4 times the cross-sectional area divided by the perimeter. So this is pretty typical way of identifying a single length scale for something that in theory has multiple. So then that allows us to calculate the Reynolds number in terms of our fluid properties, density, viscosity, and then flow channel dimensions and volumetric flow rate. So these are all things that you can know. And what is the point of all of this? The point of all of this is that, as I mentioned, this is generally used as a guide to when should you expect to start seeing the transition from laminar to turbulent flows. Just a quick point about why is this important. As we always emphasize, probably on all of our webinars, rheological properties are all calculated. And so we make a lot of assumptions about, the situation to actually make these calculations. And one of these assumptions is laminar flow or unidirectional flow. So when you start deviating from that, you can start, seeing artifacts in your data, and you want to be able to identify, when you want to know when you should be looking out for those so that you can identify them and not misinterpret them as a real fluid phenomenon. Okay, so unlike the uniform channel where our critical Reynolds number is on the order of, say, 2,500, the critical Reynolds number in the extensional channel is significantly lower, and that's somewhere around order 10. So somewhere as we approach a Reynolds number of order 10, we may potentially start seeing these secondary flows. And the most common manifestation of this type of artifact is that it looks like extensional thickening. So it looks like the viscosity is increasing with extensional rate, when in reality that's not likely the case. But what happens is these secondary flows, such as the vortices or eddy current, they actually add an additional contribution to the stress. It's not the nature of the fluid, it's the nature of the flow field. So what might that look like in the experimental data? So what we have here is, if you remember last time from last month, we talked about some data that we had on xanthan gum solutions. So just a quick reminder, xanthan gum is a high molecular weight polysaccharide, generally over 1 million, maybe even above 10 million, depending on what you have. So a very high molecular weight natural polymer. And this is in water. So what we're looking at now is the extensional viscosity. And unlike last month, I've now plotted it as a function of the Reynolds number. And we have a few different concentrations of this polymer in solution. And so what we can see is, initially we have significant thinning as we ramp up. We've represented it as Reynolds number, but in reality, what we were ramping up was the extensional rate. And we can see that it's somewhere in the vicinity of, once we get in this order 10 region, specifically somewhere around 30 or so, we can see that we have this, what looks like a thickening process. And it seems to be, consistently happening at this particular Reynolds number, with the exception of the highest or most viscous sample where we don't quite get high enough to start seeing this occur. So this, based on the Reynolds number calculation that we've done, based on this visual artifact of, apparent thickening, our best educated guess is that we are seeing secondary flows due to this inertially driven hydrodynamic instability. Okay. So moving on then to the next dimensionless group that we want to consider. And I'll just kind of preface this by saying that we just talked about the sort of inertially driven hydrodynamic instability, which is turbulence. There can be other driving forces for, similar secondary flows. And to sort of understand when you might expect to see that, that's where we bring in the Deborah number. So just as the Reynolds number, this is a dimensionless group, and we're looking at the ratio of two components that are playing a role here. The first is the fluid relaxation time, so the characteristic relaxation time of the fluid. And the second is the basically characteristic time of the flow field. So this is then a ratio of the two time scales. And this characteristic relaxation time of the fluid is really relevant to non-Newtonian fluids. So this isn't something that has much meaning for a Newtonian fluid, because, as I said, we're going to look at, other driving forces of secondary flows, specifically elasticity, and the Newtonian fluids don't have, that elastic component. They're purely viscous. So there's some ways to get this particular parameter for your samples. One of these is if you're familiar with dynamic or oscillatory measurements, specifically the small amplitude oscillatory measurements. By small amplitude, I mean small amplitude in terms of strain. So you can get an estimate of this parameter by looking at the inverse of the crossover frequency. And what I'm talking about in terms of crossing over are the elastic and viscous modulus. So if you're familiar with, say, like a Maxwell fluid, where you have a very clear crossover point for the G prime and G double prime, you can take whatever this frequency is, this crossover frequency, and invert it. And this is generally considered a measure of the characteristic relaxation time of the fluid. Alternatively, if you're doing some sort of capillary breakup, so basically looking at the thinning of a fluid element after it was stretched, and you're monitoring that thickness as a function of time, one of the parameters in the expression there is this relaxation time of the fluid. So it can come from that type of experiment as well. And then also technically you can get a gauge. I didn't put this officially on the list because it's not the best way, I think, but if you wanted another way of getting a sort of a ranking for your materials, you could use the parameters that come from fitting non-Newtonian viscosity data. So viscosity is a function of shear rate. So there are different models that you can use to fit that shear thinning, cross model, Kuroda Yasuda model. And there's the parameter in there that's relates to this characteristic relaxation time, although it's not quite as it's not really the ideal way, but it could possibly work. And then the characteristic time of the flow is just the inverse of the extensional rate. And this is the same way you'd get the characteristic time of the flow for a steady shear experiment, which would be the inverse of the shear rate, so the inverse of the extensional rate. So then the Deborah number is a product of these two, the characteristic relaxation time and the extensional rate. And so when you look at this number, if you have the ability to get your characteristic relaxation time, it can guide you in determining what is the impact of the fluid elasticity on the kinematics. And kinematics, if you remember from some of our basics webinars, is just the flow field. It's another way of saying the flow field. What is elasticity going to do in terms of the flow field? And again, we're thinking about these instabilities or onset of turbulence or secondary flows. So in general, what you'd see is when this Deborah number is small, generally less than order 1, then we're going to see something that looks like a laminar flow, where which would be like a Newtonian fluid at low Reynolds number. So no secondary flow fields present. But then when you go up somewhere around order 10 and beyond, then you can start seeing these secondary flows emerge. So again, what I mean by that are, say, vortices that might occur sort of in these regions upstream or downstream, these points that I'm sort of highlighting here on the flow channel. And these can appear, when your Deborah number is 10 or above, even when you have low Reynolds number. So this would mean then that the possibility of instabilities being driven by not inertia in this case, but by the elasticity of the non-Newtonian fluid. Okay, and then the final sort of dimensionless group that you might want to look at to kind of rank your materials or gauge your materials is what is called the pressure coefficient. And so just to remind you what the pressure profile generally looks like for the extensional channel, I've placed an example up here in the corner. So we have pressure as a function of sensor position, and we see the pressure drop before, through the contraction, and then after the contraction. And this pressure coefficient, again dimensionless, is just looking at the pressure drop between P2 and P3 relative to the total pressure drop, so P1 minus P4. So it's basically saying what is the relevance of what's happening here in the contraction versus the overall pressure drop. And the general thought behind this is that it can be used as a metric to gauge or rank what is the relative importance of elasticity or viscoelasticity effects in this contraction. And the reason it's highlighting the viscoelastic effects is that for a Newtonian fluid, this particular parameter, this pressure coefficient, is going to be independent of extensional rate. So you'll have a single value constant no matter what rate of extension you're applying for Newtonian fluid. But if you're dealing with something that's non-Newtonian or viscoelastic, then generally what you'll see is that this parameter will vary with extensional rate. And here's an example on the lower left corner where we have this pressure coefficient as a function of extensional rate. And we can see that although noisy, it's fairly constant initially, but then as we start ramping up the rate, we see that it starts to increase significantly, indicating a greater contribution of the pressure drop in this contraction to the viscoelasticity. And generally, as this value will approach 1, that's generally the max. It generally doesn't go beyond 1, as these viscoelastic effects tend to dominate the contribution here to the pressure drop. So this is just another way of sort of ranking your materials, particularly if you want to look at them as a function of extensional rate. Okay, so that's where we're going to finish off. And so I just wanted to thank everyone for joining us today, and we'll check to see if we have any questions. So well, I'll give everyone a minute, see if they can think of some questions they might have to ask. I just wanted to remind everyone that if you did sign up, within the week, you should get an email allowing you to download the presentation and recording. So if you wanted to review it and then contact us later with questions by email, we'd be happy to check in with you and answer anything that comes up later. Okay, well, I understand extensional viscosity is a little, it's new to many people, and, as I mentioned, it can be challenging, to develop even a technique to precisely control the flow field and then properly interpret it. So it is a challenge, and I think this is probably why it's less common than steady shear viscosity. But hopefully if you have questions in the future, you'll contact us and let us know. And then, as always, we do monthly webinars, so we'll be back in July. I don't think we know the topic for sure yet, but our marketing team, Eden, will be sending out the announcements for that within the coming weeks. So thank you again for joining us today. And then hopefully you'll continue to join us throughout the year at all of our webinars. Have a good day.